Let's do a trees example. This example is about Morse code, which is a signaling protocol that transmits messages by sequences of signals, and those signals are either dots or dashes. There's a correspondence between each letter of the alphabet and some sequence of dots and dashes. The problem that we'll try to solve is to implement Morse so that decode works correctly. This problem is a puzzle. It gives you an implementation of one function, called decode, along with a data representation about how Morse code is encoded in the first place. And then we have to figure out what sort of implementation of an encoding of this data would work with our decode function. So here's the encoding of the data, is that for each letter, it's mapped in a dictionary to some string of dots and dashes. Let's read decode together. It takes two arguments, signals and a tree, and it decodes signals into a letter. Okay, so decode is going to generate one letter at a time, and we're given the complete implementation. So let's try to understand decode first by seeing what arguments are passed in. We're going to define Morse, taking in this code, and here we see that code is ABCDE, a dictionary from letters to dots and dashes. And the result of that is stored in T, and T gets passed as the second argument to decode. Okay, so when we see decode signals tree, the second argument is the thing that we are generating by implementing the Morse function. What's the first argument? Well, this says decode s, t for s in a sequence of different strings. So, for example, this could be signals, a string containing dots and dashes. Now what decode is supposed to do is decode this sequence of signals into decade. It's the list comprehension that's building this list of 6 elements from this list of 6 elements. So that means the job of decode is just to generate the string E from this piece of input as signals. Okay, now we know where we're heading, we can read the implementation. So for signal and signals, what happens when you iterate over a string? Well, you get all of the different characters in the string. So signal will be a dot or a dash. This says tree is rebound to some complicated expression. We see that what it does is it takes the original tree, finds its branches, and filters them according to this condition that b.entry is the signal we're looking for. So here's another important clue. The tree that we create needs to have branches whose entries are the signals dot and dash. Now this list comprehension here is going to create a sequence of something. What? Oh, they're branches. And what are branches? Branches are trees. So this whole thing gives me a sequence of trees. And here I'm selecting just the element at index 0. That'll be a single tree. So it makes sense to rebind tree to the result of this whole expression because at least it's a tree. It's a branch of the original tree that we had before. Now this is all inside of a for statement, which means we're going to rebind this many times. Each time we're selecting a particular branch that matches the signal that's the next signal in signals. Okay, we're almost done. This says leaves is another list comprehension finding the branches in tree if not b.branches. Now not makes false true and true false. b.branches is a list. An empty list is a false value. So this is only going to be true if b.branches is empty or if b is a leaf. So what this expression does is select all the leaves in whatever tree is currently bound to. Now notice that we've rebound tree many times in order to get to this point in execution. It asserts that there's only one leaf in leaves and then returns the entry of that leaf. And what was that return value again? Oh, that's supposed to be the letter E. So now I think we can start deducing what's the structure of the tree that we're supposed to pass in. And its root is an entry that we never used. We never said tree.entry anywhere in our code. So who cares what it is? But we did say that it needs to have a branch whose entry is the signal we're looking for. So if our input is just the string dot, then it should be that there's a branch with a dot at its entry. And with only one signal, we'll rebind the tree to this subtree, at which point we'll look for leaves. And there's supposed to be exactly one leaf of this subtree, and we're going to return its entry, and we're supposed to get back the letter E. So here's a structure that would actually give back the right result for this input. And what about this input? Dot dash. So dot dash is the letter A. Following the same logic, we still don't use the root of the tree, but we would expect that there's a signal dot, which there is. That should have a branch with a signal dash. And that should have a single leaf, the letter A. Now we know the structure of the Morse code tree that we're supposed to build. It has dots and dashes when there isn't a leaf, and then it has letters at the leaves. Now, we need the alternative to encode things like B, C, and D, which start with a dash, and so we're going to have a second branch over here encoding all of that. Okay, let's build Morse. Here's the encodings for A, B, C, D, and E, which we'll pass in as the code. And by the way, here's our decode function, which we already looked through, and the tree class. So Morse says it's going to build a tree which will be returned, we'll call it the root, for every pair of letter and signal string in sorted code.items. What does that do? Well, let's try it out. If I take sorted abcde.items, I get a list of pairs sorted by the first element. Okay, so we have bound to letter A and bound to signals dot dash. We're going to trace through the tree, building it up as we go, so that non-leaf nodes encode signals, and the leaf nodes encode the letters. So for each signal and signals, we need to see whether a branch for that signal already exists or not. So if we look in tree.branches, we can filter to see if the entry of that branch is the signal we're looking for. If there's something in that match, it should be that there's exactly one such branch. And then we just change tree to be that branch. Since match is a list of trees, we need to select the tree within it. If there's no match, meaning we've never seen this signal in this position before, instead what we'll do is create a new branch. It contains that signal. We make sure that it's appended to the branches of the current tree that we're building, and then we'll continue traversing down the tree by saying tree equals branch. After this entire process, tree will be bound to the subtree within the entire Morse code tree that's supposed to have a leaf for the letter encoded by the path from the root. So we just create a new tree with that letter as its entry and add that to branches. So if we call Morse on ABCDE and then we print it out, we can see the structure of the tree we've created. The root is none. It has branches that have entries dot and dash. Dot dash leads to A, whereas dot alone leads to E. Dash dot 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 leads to B, whereas dash dot dot leads to D, etc. And so if we decode dot dash using the Morse tree for ABCDE, we'll get A. And what if we decode dash dot dash dot? Well, we'll get the letter C. And in fact, if we run the doc test here, which decodes everything in the word decade, then we'll see that it passes. So key concepts that were covered here are that the branches are a list of trees. If you want to traverse through a tree, then you can consider each branch, find the one you're looking for, and use that as your remaining tree. If you want to build up a tree, then you can do that by adding branches. And we build this tree up incrementally by traversing through the tree while appending branches at the same time.